Hello, everyone. I'm Warren Wright. I'm going to be your moderator for John Snow Labs. And today's webinar is on the state-of-the-art named entity recognition with BERT. Today's webinar will be recorded. After the presentation, we'll be sending out a link to this webinar along with a list of other upcoming webinars led by John Snow Labs. Feel free to submit any questions you may have in the question box provided. Right now, I want to introduce you to Vasil Kojaman, who will be leading this discussion. At the end of Vasil's presentation, we'll review your questions. Vasil?
Hello, everybody. Welcome to the first webinar of Spark NLP. And then in the future, we will have many of this. So it's my honor to be leading the first one. So today we are going to talk about named entity recognition with BERT. As you know, BERT is bidirectional encoded representations from transformers, which is the leading NLP architecture in the industry for the last few years. So let's get started. So named entity recognitions, in short, like NER, is a subtask of information extraction that seeks to locate and classify named entities mentioned in unstructured text into predefined categories. So why do we need NER? NER is everywhere in nearly all NLP tasks, because for the unstructured text, we need to extract some features, and NER is the main algorithm that would help us to extract those entities and the features. For example, we can extract names, persons, organizations, locations. It's very useful when it comes to natural language understanding to convert some free text into understandable structured text. So let's see in detail. So for example, as you see on the screen, there's a large sample. There are some entities that's already extracted by an NER model. So this could be some product review on your website, or some complaints, or some customer support ticket, or some just the news that you need to analyze for some other reasons. So when you apply some NER trained on some corpora, so you will get to see some entities that you are going to use for your other purposes. As you see, like the Google, IBM, Microsoft, they are all detected as organizations. And if you want to detect like the dates, so these are all useful for the other kind of machine learning problems later on. So in Spark NLP, we also have clinical NER in the licensed version. So we, for example, in that clinical NER, we have 3 predefined entities like patient, problem, test, and treatment. So as you can see, this is the identified clinical text, and then our pre-trained clinical NER model is able to extract the problems and the test and the treatments successfully. So let's talk about the benchmarks. As you know, there are hundreds of NER algorithms going on in the industry right now, but just a few of them are production ready and scalable. So let's just compare Spark NLP with the nearest competitors like Spicy or Core NLP. With the latest additions with 2.4, we had like the recent release last week, and we set new records in NER especially. So with BERT, we trained our NER algorithm with BERT, and then we got 96% dev set F1 score, which means that like the on the validation set we have 96% accuracy. This is the benchmark on CoNNL 2003 dataset, which is the baseline benchmark for the NER algorithms. And Spark NLP is the way ahead of its competitors right now. Right now, on the test set, we have 93.3, and Spicy has got 92.6 actually on the dev set. So Spark NLP 2.4 obtained the best performing academic peer-reviewed results because we developed this algorithm from the state-of-the-art paper in NER. And then we are able to train our model on CPU or GPU. It's blazingly fast. And then you distribute your job. If you have a cluster, you can train on a cluster as well. And we have easy to load pre-trained word embeddings. already included in Spark NLP, like Glow, BERT, Elmo. So this is these are the algorithms that I'm talking about. So Spark NLP is adapted from this paper, and then we also added some CRF layers on top of that. So as you can see on this paper, this was the highest state-of-the-art results in English language. So in NER systems, there are different approaches so far. So it all starts with classical approaches like rule-based, if there was no machine learning models before. So, and then people dig into the machine learning approaches, and then they treated this problem as a multi-class classification problem, and then conditional random fields like CRF. And then with the help of deep learning approaches, researchers try to dig into LSTM and then CNN and then just hybrid models. And then with the help of BERT and Elmo, right now we have very powerful NER systems. So we use this algorithm, and then on top of that, we use our own pre-trained language models to convert the words into word embeddings. Let me explain how we did this. So assume that we have one single sentence. So we have, of course, we have a labeled data set with NER. So Cohen and Al 2003 data set is already labeled. And we get the sentence. So in this algorithm, like char, CNN, BLSTM, and CRF algorithm, we call it, we create four different features from one single sentences. For example, the first feature is the tokens. So we get the word embeddings of the tokens. Like at first we tokenize and then get the word embeddings through like Glow or BERT. Today we are going to work on BERT. And the second feature is the if it's title case, lowercase, because these are all indicator of being a specific entity or not. For example, if it's an abbreviation, if it's a location, it starts with the capital letters, etc. So these are the useful features. And then we also use if this is digit or preposition, like we are using the part of speech tags. And then as a last feature, we get the chars. So which means that with the help of chars, we are able to detect the out of vocabulary words as well. If we omit one letters from this token, this word, our model would be able to detect this as the correctly label it as the correct entity. So this is the beauty of char-based algorithms. So as you see, we get we have the sentence here, and then we features, and then we concat them, and then feed into the BLSTM architecture. So as you see, this is our sentence, like the company XYZ. This is a one sentence, and we have the first level of features like the tokens, and then this will be embeddings as well, and then casing like the lower uppercase, and then part of speech, and then char features. And then we create the char features through CNN, and then we feed it into our main framework, and then like the word embeddings, part of speech, and the case features, and then char features, and then we feed into LSTM framework. So what is this Cohen and Al 2003 format? So in Spark NLP, we used a conventional NER annotation format, which is called Cohen and Al. It's the abbreviation for Conference on Computational Natural Language Learning. And in this format, all data files contain one word per line with empty lines representing sentence boundaries. For example, this is, for example, UN official equals hats for Baghdad. So we get the tokens as the first column, and then we get the part of speech tags, and then chunk tag, and then the label that we are trying to predict. On the right-hand side, we call it bioschema. Assume that we have a John Smith as a person. If you want to label this, we'll label it as to indicate the starting token. We say B, like the beginning, and then the label. And for the second and the third and the fourth, if these are all belong to the same entity, we differentiate between like I. I means that it's something after beginning. So so the model will be able to recognize this as a one single entity, as a chunk. So in New York, for example, location, these are the same. And all the others are labeled as O, like they are blank labels. So how are we going to do this in Spark NLP? We at first get this annotated data set, like CoNNL 2003 data set, and then feed into our CoNNL reader in Spark NLP, and then use our word embeddings. One of the word embeddings, today we are going to just work on BERT, but if we have time, I will show you how you can do that with the other word embeddings as well. And then we will train this data set with our NERDL approach, which is the flagship of our NER architecture. Like this is the architecture that we are going to train today. So in Spark NLP GitHub webpage, NLP models webpage, you will see some pre-trained models and then word embeddings. So we are going to use the upper rectangle for NER, and then these are the word embeddings that we already have. So you can choose any of them to train your model. Let's talk a little bit about BERT. BERT is the latest advancement in NLP, and there are many other derivatives like Alberta, Roberta, DistillNet, etc. So, which means that it is the it comes in two sizes right now: BERT base and BERT large. We have both of them in Spark NLP, by the way. In the BERT base, we have 12 transformer blocks, and the large one we have 24, and then it's already trained on 2.5 billion words on English Wikipedia, so it's already pre-trained, and it sets the new records for nearly all the NLP tasks out there. So we can call it as the ImageNet mode of the NLP. So this is the inner of BERT. So we have the words here, like sentence, and the tokens here, and then we convert the word embeddings, and then we use the decoder encoder architecture, and then we stack all the layers on top of them and then train. So which means that apart from other word embeddings, the BERT embeddings, like the embeddings for a token, depends on the context. So for the globe, for example, every word in the vocabulary gets the same vector, but in BERT, the vector representation of a word depends on the other words around it, like the sentence. So that's why we use the sentence and the tokens inside the same annotator. And BERT has 768 dimension, so it's very heavy. So let's get coding. And there's a website, as you may know, like nlpprogress.com, and these are the latest, and it tracks the latest benchmarks in every NLP test. For NER task, right now they are like the top scores belong to hybrid models, like deep learning plus machine learning, and then pre-trained language models like BERT. And right now the highest one is 93.5. And it's not production ready. It's just a research paper. And in Spark NLP, we have 93.3, which means that we have the highest industry, like a production level NER test score at the moment right now with the BERT. So maybe you will not need this, but to train this sometimes, because this NERDL model is trained on TensorFlow, so we convert this architecture as a TensorFlow graph, like we write this as a write to the disk as a graph, and then our model, our annotators in Spark NLP read this graph and then train the model. So if you have custom data sets, which is using different length of chars and the tokens and the tags, like different, like maybe you are just dealing with three labels, or you are dealing with 100 labels, you may need to create your own graph. And I will also show how you can create your own graph, because we already have that one in our GitHub page. So it's very simple. You will just state the number of the dimension and the text. And at the end, the training and named entity recognition model with BERT is as simple as you see on the screen. And then we also have a blog post coming up in the next week. So let's start coding in Jupyter so that you can see how we can train an NER. And then these are all the resources. We are going to share this as well later on. Okay, I'm going to show you how you can do that with Jupyter. But right now, this is the Jupyter Lab screen. This is exactly the same as Colab actually. You can do the same with Colab as well. So if you are having a trouble, like installing some Spark environment on your local, you can just, if you have a Google account, you can just open a Colab account and then just start coding as it's your own local machine. So the only difference would be you would already see some Colab examples in our workshop repo on GitHub page, which is free as well. So you will just need to install JDK 8 and then PySpark and then Spark NLP. That's all. And the beauty of Colab is that it offers free GPU, which means that you can train your own NER on GPU for 12 hours. And on Colab limitation is 12 hours. So it's already have a Tesla P4 GPU, and then you can just do anything that you want that you usually do on your local. So let's start training our first model on Jupyter. So okay, at the moment the version of my Python is 3.7. On Colab it's 3.6.9, so it's not a big deal. So if you wanna install, if you haven't already installed PySpark or Spark NLP, we have an article, blog post about that. Maybe you can check that, like Spark NLP installation, and then on medium.com you will see the steps. But it's the same that I just explained, like you install OpenJDK 8 and then install PySpark and Spark NLP. That's all, but you need to set your home path as well. So we just import the required libraries since we are limited at the moment. So I'm going to walk you through all the codes, like lines one by one, instead of writing from scratch. So we import some models from PySpark itself. When you install PySpark, the Spark is installed as well. PySpark is an Python API of Spark. So, and the Spark is written in Scala, and Spark NLP is also written in Scala, but we have the wrappers in Python right now. So it makes the life easier for in Python degree. But in Spark NLP, we have Java, Scala, Python, and R versions as well. So we support 4 different languages at the moment. When you import these models, you just start your Spark session. It's as easy as this one. You just write Spark NLP.start. So if you wanna train on GPU, so we have the GPU version of the models. So you will just define GPU is equal to true. So it will, the model knows that it will use GPU for training. So let's import. I just imported and then started, and then like the version is, this is the latest version of Spark NLP at the moment. We are going to have 2.4.2 so next week. So we release every 2 weeks, and then Spark version is 2.4.4, which is the latest one is 4.5 by the way. So it's the same. So we can also start manually if you already know how to start a session in Spark by Spark. You can also manually start the session and then customize your configurations. Like you can define the number of CPU that you want to use, or if you are using a cluster, you can just define the number of the pods and the nodes here, and then define the maximum driver memory, etc. This is what's going on under the hood when you run start. So this is the same as this one. So I'm not going to delve into, but it's exactly the same. So if you have a problem or some limitations, or if you get some errors, like some buffer max error or memory error, depending on your configuration on your local machine, you can just go back, restart your kernel, and then start the Spark session manually, because you need to get or create this Spark session before starting to work in Spark NLP. Let's download CoNNL to 2003 annotated datasets. So we will train on train, and then we already have this in our resources in GitHub. So you can just download manually, or you can in Python you can just use this module, and then it will download. So when you do that, for example, let's delete the downloaded ones and then download again. So as you see, we downloaded both. So let's see how it looks. So this is the CoNNL that I'm talking about. So it starts with every document starts with this line, and then every word, and then part of speech, and then the label. These are labeled by human. So at the end of this webinar, I'm going to also show how you can create your own training data set. So this is how it looks when you open train dataset. You can also read this with like a file reading in Python. So let's create the first NER pipeline. So since this is CoNNL format, we need to convert into Spark environment. Like we need to put it into the Spark session with the relevant columns, fields already created for us. So we are just going to use the tokens and the part of speech and the labels coming from the dataset, and then read this dataset with a CoNNL module that we already have in Spark NLP.training package. So you are going to use the same one. So you will just read this one with CoNNL reader, and then it will create. Let's see. Okay, it's done. So which means that it just split it up this training data set, like creating the text, document, sentence, token, part of speech, and label columns. So it didn't have any text or document or sentence column beforehand, but our CoNNL reader already converts this, because these are the columns that we are going to need to vectorize. For example, we would need sentence column. We would need document to feed anything inside Spark NLP. So these are already handled by our CoNNL model. And we have 14K sentences at the moment. So like the number of rows. So let's load the BERT. We have the BERT embeddings, annotators coming from Spark NLP.annotator. This is one of the embeddings that we have. Like we have Elmo embeddings, BERT embeddings, word embeddings. We have 3 different types of word embeddings in Spark NLP. So we are going to load BERT base cased. As you know, there are different variants of BERT, like a BERT base uncased, BERT base cased. So which one to use depends on your use case, train set, and the complexity of the text that you are trying to model. So, and we have different, as explained by the authors of the official BERT paper, different BERT layers capture different information. So, for example, right now we are going to use the fastest one, which is 0. But if you want to use tooling layer -1 means that the last layer, which is the slowest one, and the -2 is the second to the last hidden layer. So it all depends on your use case, which one to use. But if you want to get the real power of BERT, you need to use the last layer, or the -2 as the second to last layer maybe, and then it would train longer and heavy, but at the end you will get a most accurate model that you could have. So it all depends on your use case. So let's Let's load it. When you write this one and then write the name of this one, it will be downloaded to your local cache from Johnson Labs AWS S3. So it will be just downloaded from their public model because it's free. And then we define the number of the columns, like the input columns, the name of it, because as I mentioned before, BERT embeddings are context aware. So we need the sentence and the tokens coming up. So each token will get some different representations depending on the sentence that it's in. So the produced column will be called BERT. So you can write anything here. And you can set this off and on like a case sensitive or not. And the pooling layer is 0. When you do that, you will just, when you do that, it will download 400 megabyte of file to your local, which is already downloaded, which means that it will just check if it's anything updated on the remote. If it's not, it will just use the one in local. So it's already downloaded to my local, so I'm going to use that one. So if you want to use something different, you can also use BERT embeddings.load instead of pre-trained. I'm going to show that if we have time. So yeah, this is the example. You can just write load and then local path if you already have this, download this from somewhere else, which is Spark NLP compatible, of course. Now let's read the test set. Why do we need test set? If you want to measure, like test your trained model on an unseen data set, you need to use another test set, and you can just define like the read in the same way with CoNNL, and then using the BERT annotator that we created here, you need to transform it because it needs to have BERT column, because it needs to have these features while we test our NER on an unseen data set. So you will just transform this data set with the BERT annotator that we just download, like, and then it will just, it's very fast, by the way. Let me show you. It's just reading test data set from my local and then create the BERT embeddings column. So which means that we already have the embeddings for each token right now. And let's see the first 20 rows. As you see, these are the tokens from test set, and these are the embeddings for each token, and then the labels that we have, like the ground truth labels. And if you can just convert this to NumPy, I just converted to make it like much prettier for you. It's a 768, so as many as the token numbers. Now we are on the heart of this NER, which is called NER-DL approach. NER-DL approach is one of the annotator approach in Spark NLP. You can read all about this annotator, transformer, estimator, and annotator approach concepts in medium.com Spark NLP channel as well. There's a long article explaining all these differences and how Spark NLP works. So we just load this one, like define this one, and then set the input columns. We already have the sentence and the tokens and the BERT columns, which is already created. Now we will define our label column, which is already, when we read our train set, it's already there, like label column is at the last column. And then the predicted column will be NER, so you can write anything here. This will be just a name of a field. You can train, you can set the maximum number of epoch here. You can define like 1, which is like a most primitive one, and then you can define like 100. So anything you want, like as many epoch as you want. We can define learning rate or learning rate decay coefficient. Why do we need that decay coefficient? Like a scheduled learning rate based on the epoch. So it will change the, like it will schedule some learning rate based on the epoch. And then you can define the batch size. So all these parameters, hyperparameters, will affect your end result. So you may think of like a hyperparameter optimization. So you can go back and change this and then train again if you are not satisfied with results. So when you set the verbosity to 1, there will be log file written on your root folder, local folder, or home folder. And then you can just check that txt file or log file, and you see all the validation scores, all the epoch results, and then test set. So after each epoch, it will be test on the test set as well, which is defined here. That's why I load the test set and then created the embeddings and then wrote to disk. When I did this, I can just define this test set on the test set parameter. So it after each epoch, it will test the trained model on this unseen data set. So you can also like on and off do this logging mechanism as well. And then you can also get the confidence scores for each predictions in your metadata. Then since right now we have the BERT annotator, and then narrow the other approach. So we can just tag these two annotators inside the same pipeline as we do with sklearn. This is a pipeline for PySpark. So we just told our pipeline that we are going to send you a Spark data frame, and then you will at first use the BERT annotator, and then the end result will be fed into the NER tagger, which is NER DL approach. We can just run this cell, and then as you see, I just, for example, did some tests. Like you can just, if you want to see some faster results, you can just use the first 1000 rows of your training data. And it took on my local machine, it just took 45 seconds. So which means that you can train 1000 lines of training set with state-of-the-art BERT architecture and then NER architecture without GPU on your local machine with 45 seconds. So it's pretty fast. So and I'm using the pooling layer 0 at the moment, by the way. So I just did this with like, what if I train this like entire train data with 10 epoch, which is usually enough for any NER, for our NER model, by the way. On GPU with layer 0, it takes 30 minutes to train, which means that if you want to have a very reliable, like a decent, let's say, a decent NER model trained with BERT, it will give you the results with 30 minutes for free on GPU on Colab, actually. So you will just start with the GPU support. Now we have the NER model trained. Let's not wait 45 seconds, and then let's just jump into train. Let's assume that I run the cell, and then I have NER model. Let's say, as you see, it's the model, like the pipeline model. So let's get the predictions from the test data from the first 10, or we can just say like get all, because it doesn't matter, because Spark, it's an lazy evaluation, so it will just show as many as I define in show. So it's getting the predictions. So the predictions are ready. So let's see what's going on in like a pretty version. So this is the predictions that I already got. So let's check the results. These are all struct type. I already explained all these concepts in the article, in Spark NLP article. So these are all created right now. These are the ground truth, like the middle column is the ground truth. These are the tokens from the test set, and these are the results that I already have. So this is just one epoch for 1000 rows. These results are coming from, by the way, which means that, let's see, much prettier here. So this is the test set, and the predictions are coming from one epoch for just 1000 rows. So as you can see, it's not that strong because it's just one epoch. So let's load the one that I trained with 10 epoch. I already have that. You can just load that one from disk. I just trained this today, like 10 epoch. It took like 30 minutes on Colab. So I just loaded it and then get the predictions again. You see, after 30 minutes, this is the thing that I got from unseen test set. As you see, this is not correct, wrong prediction, but these are all correct, like, as you see. So which means that in 30 minutes, you get a decent NER model, because when you tune the parameters and then train further, of course, you will get, and then, of course, when you use the pooling layer like -2 or -1, you will get way better results. Let us see. We can convert this to pandas, and then we can convert this Spark data frame to pandas, and then you can also view this one, and then you can do some classification report or confusion metrics as well. So what if we do, we change the set pooling layer to -2, which is the real BERT. So that's why Google is making so much money on TPUs at the moment. So which means it requires huge computation power, but it's when you have the cluster or a decent GPUs on your system, on your cluster, it will not be an issue. For example, it will just in 1 minute, if you have a nice GPU, like a decent GPU, in 1 minute you will get 1 epoch, maybe. I think in Colab it's 7 minutes, I think, per epoch. So we will just change the pooling layer and then rerun the pipeline and then train again. And this is for just 1 epoch with pooling layer 2. As you see, it's getting better when you change the pooling layer. So now we are done with training our NER model with BERT with different configurations. So if you want to do that with glow embeddings or any embeddings that you would have, you may have trained your own word embeddings model with Janssen, for example, and then you can load it into Spark NLP easily. For example, we have the word embeddings model. You can just do the same exactly and then replace that BERT embeddings with the word embeddings, and then run this again. All the steps are same, so you just run, train, and then you get some similar results as well. So this is coming from 100 dimension glow word embeddings. I think we are out of time at the moment. I can keep going, but I can take the questions as well. One last thing, you can save the model to your disk, like the trained, because these are the stages. Like we have 2 stages, word embeddings and NER-DL models. You can write the stage 1 to your disk and then load back, and then using your prediction pipelines later on. Thank you very much for listening to me.
Basil, thank you. We do have one question for you. It is, do we have BioBERT available in Spark NLP?
Yes, we have. We already have it. We can just, for example, check. Let me show you on Spark NLP, John Snow Labs models. This is open to public as well. These are all the pre-trained models. We already have BioBERT, clinical BERT. Like, yes, we have the trained BioNLP as well, and we have the but BioBERT is in licensed version, so you may not be able to use that in the free version. But we have the BioBERT, clinical BERT, 4 different bio version of the BERT, and then we have different versions of the pre-trained NRDL.
Okay. All right. Thank you very much. Now, today's webinar, like we said, is recorded, and we'll be sending out a link to this webinar along with a list of other upcoming webinars led by John Snow Labs. Thank you very much for your attention. Appreciate it.
Yeah, I think.